Hello, everyone. My name is Scarlett, and I am in the Survey of Astronomy course with you all. And I'm also taking an honors class, which let me do an independent study. And I chose to focus on Hawking radiation within this course for that. So throughout this video, I'm just going to be explaining everything I learned about Hawking radiation. And this theory plays a big role with black holes. So we're also going to be talking about the anatomy of black holes and all the different parts that goes into it. So, to just start it off, let's look at the anatomy of a black hole. So, the most important part of a black hole in the context of this theory is the event horizon, also known as the surface of a black hole. But to make this easier, I found this good visual from NASA. So, it really helped me understand the different parts. So, looking here, we can see that the event horizon is right there, and that is the surface of a black hole. It's kind of the end all be all of one. Once you cross this point, you have to move faster than the speed of light in order to escape. And that's why black holes are black, because nothing can escape them once it has entered. Then we have the event horizon shadow, which is roughly 2 times the size of the surface of a black hole, and it's created because the black hole has such a big mass that it warps the gravity around it, causing all of the other objects in light to rotate around it as well. If you imagine the black hole being a bowling ball and you set it on top of a sheet or even a trampoline, it's going to weigh that down towards the middle, causing this huge warp. And then all of the particles are just going to orbit around that. And so that's what this event horizon shadow is. And because the event horizon takes in all of the light, not letting any of it escape, that's why it's also black. Then we should talk about the accretion disk, which is this whole disk that's orbiting the black hole here. And this is just all gas, particles, and other matter from stars or celestial objects that have strayed too close to the black hole's gravity field. And they orbit the black hole. And when I was originally researching this, I thought, why doesn't this accretion disk just get sucked into the black hole if the black hole sucks everything into itself? But because all of the particles in this disk are moving so fast at such high velocities, they're able to resist that pull just enough to orbit around the hole until they get to those inner layers, and that's where they are sucked into the black hole. And in addition to the high velocity allowing them to orbit, that high speeds also creates a lot of friction within these particles because of that kinetic energy. Everything's bumping into each other there. And that's where we get the light, as that heat source is turned into visible light for us to see. And the accretion disk is the main source of light for the black hole because everything's moving so fast, it creates light. Then Doppler beaming is an effect that the black hole accretion disk has, because if we think back to the light chapter of the Doppler effect, where things moving towards us seem brighter, things moving away from us seem dimmer, that's just exactly what's happening here. The particles streaming towards us appear brighter and bluer compared to the particles moving away from us. They seem dimmer and redder. Now, the inner rains look brighter because they are moving faster, because they have less of a space to orbit, but that's just the effect of Doppler beaming. Similar to a train moving past you, as it comes towards you, it's got a higher pitch compared to it moving away from you. It's got a lower pitch. It's just what's going on. It is important to note that not all black holes have an accretion disk. There are some dormant black holes that don't have this if there are no stars or objects nearby to be sucked into that field where they orbit. So a black hole's dormant when nothing's feeding it, really, but it can be awoken again if something strays too close and does fall into its orbit, reawakening that black hole and recreating that accretion disk. Then we have the photon sphere here, which is right outside of the event horizon, and it's just particles of light from that accretion disk quickly orbiting that event horizon shadow before falling into the event horizon. And a photon is just a particle of light moving through the electromagnetic spectrum. So it really is just particles of light quickly orbiting before they fall into that event horizon. Then we have the corona up here, which you can see well in these photos on that image on the left. That is a good visual of the corona, which is formed because the black hole is huge. It has such big mass that creates an equally large magnetic field around it, and that field moves through the accretion disk, pulling those particles up and down with it, respectively, and creating this huge turbulent cloud of 1 billion degrees, moving at almost the speed of light, releasing X-rays, and it's just known as the most physically extreme environments in our universe because of how hot and fast and aggressive it is. Yet we still don't know that much about coronas. We're still trying to figure out their characteristics, sizes, just a lot of things about them. Similar to that, we have these particle jets, which are featured well in these two photos. Again, we don't know a ton about them, but we know that they are formed from the inner layers of the accretion disk, and it's just these fast-moving particles that have been rerouted from the accretion disk, moving in opposite directions from this black hole, and they move close to the speed of light, and they do come from all different sizes of black holes, but the supermassive black holes, like the ones in the center of our galaxies, can be up to 100,000 light years long, moving close to the speed of light. So they are, again, very aggressive, fast moving jets of particles. So the name makes sense there. And then we have the point of singularity. And this is right in the middle of the event horizon. It's the center of a black hole, and it's the theoretical point where we believe that everything that has entered this event horizon is just crushed into infinite density. Where if you imagine our sun just crushed to the size of a grain of sand, that's how dense we're talking in here, if not more. So we think that inside of a black hole, everything is just crushed to the sphere of infinite density. Now, it is important to note that a lot of this research is super new. We're still learning a lot every day, every year, even. The first photo of a black hole wasn't taken until 6 years ago in 2019. We were able to get close enough to get a visual on one. The first measurement of a black hole wasn't until 10 years ago, where we were able to measure two black holes colliding. So a lot of the research around black holes is still being formed. That's why we don't know a lot about the coronas and particle jets. We don't know what's inside of a black hole because we can't just go in there and find out, right? So it's just important to realize that a lot of this is still being worked upon. So now that we understand what makes up a black hole and the different parts to it, we can get into the topic in which I study, which again is Hawking radiation. And it was theorized by Stephen Hawking, which is a famous physicist, and he thought of it in 1974. And before him, it was understood that black holes are black, right? They don't release or emit any particles once they've entered that event horizon. Nothing escapes them. They're just black. But Hawking changed this in 74 when he started thinking about quantum fluctuations and quantum field theory, which say that essentially the universe moves in these waves of energy, and they fluctuate or kind of jitter, trying to find equilibrium, balance. And sometimes, in order to maintain that balance, they spit out these particle antiparticle pairs, as shown in these images here, these little circles, these particle antiparticle pairs that are spit out, but they're equal and opposite charge of each other, and they immediately annihilate each other to go back into equilibrium. So they exist on borrowed energy from the universe in order to rebalance that energy. And when they annihilate each other, they give that energy back to the universe all as well. So Hawking was wondering, what would happen if these particles popped up right on the event horizon of a black hole, right on the surface? And he thinks that the negative charged particle would fall into the black hole while the positive one escapes, becoming radiation, which is again just another form of energy transfer in the magnetic spectrum. So he thinks that the negative one falls in, the positive one escapes, becoming the radiation aspect of the theory. But these particles no longer can annihilate each other, giving that energy back to the universe because they're split up. So the energy debt has to be paid back somehow. You know, these particles are existing on borrowed energy, borrowed time. So someone has to repay that debt in this event, i.e., the black hole pays it back. When it sucks in that negative particle into the vacuum, the black hole uses its own mass and energy to repay that debt to the universe. And you can see that easily in both of these where the particles are separated, and that black hole uses its mass and energy to rebalance the universe's energy, but then it loses its mass in the process. And if we think about it, if this takes place in a dormant black hole where there is no accretion disk, the black hole isn't feeding, it's not gaining mass, and it's losing its mass because of these virtual particle pairs, then the black hole would evaporate because it's losing its mass, it's not gaining anything. So our black holes would evaporate. And yes, it would take longer for one to evaporate, longer than the universe has been in existence, but it would still happen. So then we have to wonder, where does everything go? Where does everything go that the black hole has sucked up and, in other words, eaten throughout its lifetime? Because quantum mechanics says just like energy can't be destroyed or created, neither can information. Now, information is just the data we use to describe anything physical in our universe. It's the instruction manual to anything. Think of it this way. Imagine you have a piece of paper and you write a little note on it, but then you burn that piece of paper in a fire. If you were to gather all of the ash, capture all of the gas and the heat energy released in burning that piece of paper, and you had the information about it, you could replace all of those atoms, particles, everything that makes up that paper in the exact order that it once was, recreating that piece of paper if we had this technology, but information allows that to happen. It can't be destroyed, it's always there. But if these black holes are evaporating into nothing, that information is lost. We don't have it. So this all leads and is defined as the information paradox of Hawking radiation because it just goes against what we know about quantum mechanics. So Hawking radiation really shines a light on the fact that we don't have a unified law of the universe. It shows where gravity and quantum mechanics start butting heads because they can't both exist at the same time, and they really start fighting here at Hawking radiation. If black holes are evaporating, where is that matter and information going? So the Hawking radiation hasn't been directly observed yet because we can't get close enough to a black hole to see it firsthand. But it has been observed in lab procedures. In 2018, scientists from the UK and Italy designed an experiment shown here in the bottom right, where they took this glass block and they shined an infrared laser through the block at a high speed, essentially changing the way the glass moves and interacts with other particles. And then they measured the photons being released, and all of the extra ones that they witnessed, they think is Hawking radiation. It shows the change of the particles, and this glass block mimics an event horizon. So we don't have the ability or technology to create a black hole on Earth, nor do we want to if we could. Doesn't sound like it would end well. So they created this artificial event horizon and witnessed Hawking radiation taking place on it. So Hawking radiation has been observed in the lab, and we do have telescopes on Earth that would be capable of detecting these radiation particles if they were to hit our atmosphere. But this would have to happen under a very specific set of circumstances. The black hole would have to be lined up with us. The particles that were released, the positive one that lost its pair and was released as radiation, would have to hit our atmosphere. At the same time, we're using these telescopes to monitor radiation of the atmosphere because they are moving at a different rate than any other particles hitting our atmosphere. We should be able to detect them. It just hasn't happened yet. Now, if we are able to detect Hawking radiation, it could lead to a unified law of our universe or maybe new particles that we don't even know exist yet, and possible new physics theories relating to the universe. And it would just be a huge breakthrough in everything. So I found this topic super interesting. The fact that these particles jump in and out of existence, annihilating each other, leading to the evaporation of a black hole, and kind of making us just question what we know and really proving how much we know about the universe and yet how much we don't know at the same time because we're still learning so much. So this is such a cool time to be researching everything and learning what we are. So I hope you found this as interesting as I did, or were at least able to make it to the end of the video. Thank you guys.